Okay, 4 o'clock. Well, 4 o'clock Eastern time. Our speaker is James Flemings from the University of Alaska, Anchorage. He'll be speaking on modular monochromatic 3T colorings. Go ahead.
All right. So, yep, my name is James Flemings, and today I'm here to give a talk about modular monochromatic 3T colorings. So first, I want to start with a well-known combinatorial problem called the lights out puzzle. So we are given a 5x5 grid where each square represents a light that is either on or off. And the goal of the game is to turn off all of the lights. Now, if you press on a light, not only does that light change state, but so does the lights adjacent from the top, bottom, left, and right. So for example, suppose we are given a 5x5 grid here, and I were to press the lights, and all the lights were turned off, and I were to press the light 7. Not only would 7 turn on, 2, 6, 8, and 12 would turn on. And if I were to press the light 25, 20, 24, and 25 would turn on. Now, if I were to press the light 19, 14, 18, and 19 would turn on, but 20 and 24 would turn off. And so we can represent the lights out puzzle as a graph where each vertex corresponds to a light in the puzzle. And we can color each vertex based on the number of times we press that light modded by 2. So for example, if we had pressed the light 7 once, we can color the vertex V7 1. If we pressed a light 0 times, then we can color a vertex 0. If we had pressed 7 3 times, well, that is equivalent to pressing a light once. It'll still turn on 7 and the adjacent lights. And so we can just color that light 1 as well. And so modular monochromatic 2-0 colorings were previously studied and used this idea of turning on and off lights with the lights out puzzle. And 2-0 colorings are closely connected to dominating sets. So if we have 2 sets, S and T, where S is the set of vertices colored 0, and T is the set of vertices colored 1. Suttner's theorem states that every graph contains an odd dominating set. So if T is an odd dominating set for a graph G, then every vertex V of G is dominated by an odd number of vertices in T. So this implies then that every vertex can be dominated an odd number of times. Thus, 2-1 colorings for an arbitrary graph G are trivial. And so we can extend this lights out puzzle to 3 states. We have an on, dim, and off state. For example, if we press the light 7, that would turn 2, 6, 7, 8, and 12 to dim. And if we were to press 7 again, then 2, 6, 7, 8, and 12 would turn on. And if we were to press 25, then 20, 24, and 25 would turn to dim. And again, we could represent the 3-state lights out puzzle as a graph where each vertex is colored the number of times it was pressed, mod 3. So 7 could have been pressed 2 times to turn all of these lights on, or it could have been pressed 5 times, and so on. And so we can just color that 2 to represent that. And same with 25, it could have been pressed 1 time or 4 times, and to represent this as dim. And so we can just color V25 as 1. So for modular monochromatic 3-1 colorings, our problem of interest is to find, if possible, a set S of vertices of a graph G, so that if each vertex in S is pressed a certain number of times, then all of the lights of G will be dim. Alternatively, we can define a coloring C that maps the vertices, or maps each vertex to an integer value, modulo 3, and that induces a coloring sum that's defined by sigma of V, which is equal to taking the coloring of each vertex in a closed neighborhood of V and adding them all together. And we want to know if there exists such a coloring that makes every pair of vertices in G makes their coloring sum equal to 1. So for example, suppose we have the path of order 3. If we color the vertex 1 to 1, then we will, and look at the coloring sum for each vertex, we will see that the coloring sum for each one will be equal to 1. For example, the coloring sum for V1 would be the coloring of V1 plus the coloring of V2 plus the coloring of V3, which will be 1 plus 0 equals 1. And so since each coloring sum for each vertex is equal to 1, we can say that this is a 3-1 coloring for P3. Now, something interesting happens when we take P3 and apply a 3-1 coloring to it, and then take another P3 and apply a 3-1 coloring to it, and connect the vertices that are colored 0 in each P3 in this way. And if we do this, we achieve a 3-1 coloring for the cycle 6. And we can do this for any arbitrary number of P3s. And so we can generalize this and say for every C3, or for every Cn, where n is divisible by 3, there is a 3-1 coloring. And that coloring will be the following. We can color every third vertex 1, starting at V1. So the coloring of V1 will be equal to 1, the coloring of V4 will be equal to 1, all the way up to Vn minus 2. And then we can color the rest of the vertices 0. And that will give us a coloring sum equal to 1 for every vertex in Cn. Now, if we look at C3 with this 3-1 coloring, we notice that there could be, that we can achieve another 3-1 coloring that is different to this one. Specifically, if we color V1 and V3 equal to 2 and then V2 equal to 0, the coloring sum for each vertex will equal 4, which mod 3 will equal 1. And so this is a valid 3-1 coloring. And there is also another 3-1 coloring that we can do. We can color V1 and V2 equal to 1 and V3 equal to 2. And this again will give us a coloring sum for each vertex to be 1 or to 4, which mod 3 will be equal to 1. And so if a graph contains a 3-1 coloring, it is possible that there could be multiple 3-1 colorings for that graph. So if we look at C3 again with this 3-1 coloring, let's do the following. Suppose we double the coloring of each vertex. So take the coloring of V1, which is 1, and let's double that. That will give us 2 times 1, which will equal to 1, which is equal to 2. And if we take the coloring of V3 and V2, which is 0, and we double that, those two vertices will go to 0. And if we look at the coloring sum then for each vertex, it will equal 2. And so what we have done is achieved a 3-2 coloring from a 3-1 coloring just by doubling the coloring of each vertex. If we take a 3-2 coloring of C3 and we double each coloring of a vertex, we get the following. If we take CV1, or the coloring of vertex 1, and we double it, we get 2 times 2, which is equal to 4. But 4 mod 3 is equal to 1. So the new coloring of V1 now will be 1. And if we do this again for V2 and V3, we will see that the coloring sum for each vertex becomes 1. And so again, we have achieved a 3-1 coloring from a 3-2 coloring just by doubling the coloring of each vertex. And so we could generalize this and say every 3-1 coloring can be converted to a 3-2 coloring by doubling the 3-1 coloring of every vertex. And conversely, every 3-2 coloring can be converted to a 3-1 coloring the same way. So if a 3-1 coloring is found, then we have also found a 3-2 coloring. So let's look at hypercubes now. Hypercubes, each vertex in a hypercube can be represented by an n tuple of 0s and 1s. 2 vertices are adjacent to each other if they differ by 1 position. So in this case, for example, 110 is adjacent to 111 because they differ in the rightmost position. So we'll define some notation here. Let IV be the number of 1s for a vertex. And this will be important for our colorings. Let L be the set of vertices such that IV is equivalent to 0 mod 3. So the number of 1s is 0 mod 3. Let M be the set of vertices such that IV is equivalent to 1 mod 3. And let N be the set of vertices such that IV is equivalent to 2 mod 3. So if we look at hypercubes where the order n is divisible by 3, we can define a coloring C by the following. the coloring of VI is equal to 0 if VI is an L. So the number of ones in VI's n tuple is 0 mod 3. If that's the case, we'll color it 0. If VI is an M, we color it 1. And if VI is an N, we color it 1. So for example, if we look at 111, the number of ones in this n tuple is 0 mod 3. And so it's colored 0. And it's adjacent to 3 vertices colored 0. And so its coloring sum then will be equal to 0. And if we look at 001, that vertex is in M. And so we color it 1. And it's adjacent to 2 vertices colored 1. And so its coloring sum then will be equal to 0. So we're going to show that the coloring sum of VI in M for all the vertices in M will equal 0. But to look at L and N, it'll be very similar. You can follow the same procedure, and it will also come out as 0 as well. But if VI is an M, then we know that the number of ones, or IV, is equivalent to 1 mod 3. And then VI could possibly have this n tuple. So VI has 1 mod 3 number of ones and 2 mod 3 number of zeros. Remember that vertices are adjacent if they differ by 1 position in their n tuple. And so if we were to change one of the 1 mod 3s to a 0, then that is a vertex in L. So there's 0 mod 3 ones in that n tuple. So if for every 1 mod 3 we change, for every 1 mod 3 in this n tuple, it is adjacent to a vertex in L. And so we can say then that VI is adjacent to 1 mod 3 vertices in L. Likewise, if we change a 0 to a 1, then that is a vertex in N. And so if we change, so for all the zeros in the n tuple, that is a position that is adjacent to a vertex in N. So we can say then that there are 2 mod 3 vertices in N that are adjacent to VI. And if we look at the coloring sum of VI, that is just the coloring of VI plus this term, which goes to 0, times the number of vertices in N, or plus the number of vertices in N times the coloring, which will give us 0 mod 3. So currently, we're investigating the Peterson graph, and we had just looked at a bunch of other common classes of graphs, and we're looking to see if a 3-1 coloring exists, and if so, what that coloring may look like. And we welcome any suggested graphs to further investigate. I want to conclude by thanking my mentor, Eric Andrews, for his mentorship and guidance on this research project. Also want to thank Chira for allowing us to further investigate her work on modular monochromatic colorings, and also for this conference allowing me to give this presentation. Are there any questions?
I just have a basic question about the, I guess that 5 by 5 square grid that you started off the talk with. If you consider what kind of graphs or hypergraphs you could end up with if you had a different shape, but you kept the same rules, like if it was a triangle or a rhombus or, you know, something else instead.
What was your question again? Sorry.
Has there been any work on like what kind of graphs would you'd get if, you know, if it wasn't a square, if it was a triangle or a pentagon or a hexagon or something, same rules, same on-off switch setup,
Oh, okay.
but different shape besides a square.
Okay. Oh, yeah. It really just depends on how you want to define that adjacency, I guess, because if you had a triangle, then you can see what squares then would be adjacent to each other, because ultimately, just from the lights out puzzle, we were able to create a graph out of it, and we defined the adjacency from those graphs just by the top, bottom, left, and right lights, but we ignored the diagonals. They are adjacent to those vertices in the diagonals, but we didn't count those. So I guess it would just depend on how you would define it. I'm not too sure though if there had been any research though in that.
Right.
Okay, if there's no more questions, you're welcome to thank the speaker by clicking on the reactions button